So, good morning, everyone. I'm Hyoungwook from UIUC. Today, I'm going to present our MeshSlice, which is 2D tensor parallelism method for distributed DNN training. So there are three dimensions of DNN parallelism, and for large-scale DNN training, mostly LLMs, you need to use all three of them: data parallelism, pipeline parallelism, and tensor parallelism. Here we are focusing on tensor parallelism because it is a bottleneck. It causes the most communication costs because you have to communicate the shards at every layer. So because of that, it's mostly limited to 8-way tensor parallelism in clusters. So our problem is, how can we enhance the scalability of tensor parallelism? So one solution for that is using two-dimensional tensor parallelism. So here I'm comparing 1D tensor parallelism to 2D TP. So if you do 1D TP, a shard needs to be communicated to all other chips. But on the other hand, in 2D TP, because the chips are laid out in a mesh, a shard needs to be communicated to only its row or only its column. As a result, it's reducing the communication cost. The objective here is to use 2D tensor parallelism and expand our 3D cluster to 4D, 2D TP plus DP plus PP, so we have better scalability. The core of 2D tensor parallelism is 2D matrix multiplication algorithm, or 2D GEM. I'm covering some basics here. So the accelerators are laid out in a 2D torus connected with inter-chip interconnects. The matrices are partitioned into shards, and each shard is stored locally in the accelerator memory, like A00 to Z22. As explained before, the matrices flow. One of them flows horizontally, one of them flows vertically, and one of them remains stationary. And what flows where defines the data flow of 2D GEM. At the end, each chip holds a shard of the output matrix. Optimizing 2D GEM has a few parameters. First, you have to choose the algorithm itself, because distributed 2D GEMs have different types of algorithms, and the choice is critical. Second is the data flow. Depending on what remains stationary, there are three major data flows of 2D GEM, and this choice of the data flow defines the traffic pattern of your 2D GEM. Last but not least is the mesh shape, which means the number of rows or number of columns in the device mesh. The mesh shape is very important because it determines how much traffic you're incurring during the 2D GEM. Note that square is not always the best. You need to find a great shape for each gem. Given these motivations, the major contributions of this work are: first, we're proposing MeshSlice, which is a novel 2D GEM algorithm that solves inefficiency problems of existing ones. And we also propose LLM Autotuner that finds an efficient combination of data flow, mesh shape, and communication granularity automatically. And we implement MeshSlice on TPU clusters and evaluate its performance for LLM training by simulation. So Google is already using 2D tensor parallelism using collective communication operations. This is the timeline of such collective 2D GEM C-AB transpose. Here, A remains stationary, B flows vertically, C flows horizontally. First, we have to vertically all gather B shards. Then, as you see in the blue, you have to do AB transpose of the shards to get the partial outputs in the orange. Finally, we scatter these partial outputs and accumulate them into C shards locally stored in the accelerators. In the total, you can see the execution time takes this amount of time. You note that these communications are not overlapped with computations. That's because these communications have true dependence with the computation. This blocking communication is a significant problem. This communications may take up to 40% of total LLM training time in modern LLM training clusters. Well, Google has a partial solution for this. Wang et al. Proposed partitioning the collective communication into partial communications, like in this case, this reduce scatter operation is partitioned into shift operations like this, and apply software pipelining so we can overlap computation with communications. As a result, we're running in a shorter time, but you can see that the altogether is not overlapped because this method is only applicable to one of the dimensions. So, although natural question is, can we apply such partitioning to both dimensions? Well, the answer is yes. We already know the answers, but those answers have efficiency problems. There are two known ways to partition collective communication into partial communications. The first method is, as we saw, partitioning it into circular shift operations. If you apply this to two dimensions, this results in Cannon's algorithm. This is a base algorithm for systolic arrays, so you can think about the systolic arrays. Well, Cannon has two efficiency problems. First, you need to skew the shards before doing the computation, which is extra communication cost. And it only supports square mesh. And as I mentioned, square mesh may be inefficient for traffic cost. The second method is to partitioning them into all gather to broadcast and reduce scatter to reduce operations. This approach results in SUMA algorithm. SUMA solves Cannon's problems. It doesn't skew. It supports any mesh shape, but it still has inefficiencies because it creates a lot of fine-grained communications. And because of that, it offers a lot of synchronization overhead, which is very inefficient in super high bandwidth interchip interconnects now. So our proposal is the third partitioning method for the first time, which is partitioning into multiple all-gather and reduce scatter operations. This is called MeshSlice, as is shown in the far right of the figure. The key idea is slicing the shards into subshards and apply all-gather or reduce scatter to each subshard at each iteration. By configuring the number of slices as, it supports control of flexible communication granularity as a parameter to optimize. But the key challenge here is how can we design the correct one, because arbitrary slicing may result in an incorrect jam algorithm. So let me visualize how this slicing and algorithm works here. This is the same C equals AB transpose jam, where A remains stationary, B flows vertically, and C flows horizontally. So because we have three-way slicing, it's done in 3 iterations, and I'm showing the first iteration first. So this iteration begins with slicing the B by its rows. So we're taking every third row of B shard, as shown in purple color right here. And this subshard, purple subshards, are all gathered vertically, just like before. And just like before, we apply AB transpose, which will become this column subshards of the partial outputs, colored in purple. Those are the same third column of this partial output. And then this partial output is reduced scattered, forming a subshard of C, and accumulated to the subshard memory space C in local accelerator. So if you move to the second iteration, everything moves one shift. So we're doing the same algorithm, repeating same algorithm for the second subshard, colored in yellow. So as you see, the B we take every third row, but shift it by one row. C will accumulate to every third column, shifted by one column. So if you see the timeline in the middle, this shows what happens if you apply software pipelining to these 3 iterations. Look at this time interval T0. So we're computing all gather of the last iteration, compute of the second iteration, and reduce scatter of the first iteration at the same time asynchronously. As a result, most of the communications can be overlapped with computations, and it's reducing the total execution time significantly. And you can control the number of slices as you think. If you have more slices, you will have less unoverlapped portions. But it may increase the synchronization cost, so there's a trade-off that's solved by AutoTuner, which is in the paper. So we're benchmarking the LLM training performances of 4 2D gem algorithms, MeshSlice, Summa, Wang, and Cannon here. So we simulated TPU clusters up to 256 chips. Here we compared flop utilization, which is directly proportional to the performance itself. And in the x-axis, we are applying weak scaling. So we are increasing the chip count from 16 to 256, as well as the batch size, because that's the natural way you scale in LLM training. So you can see MeshSlice is always better than the baselines, regardless of the size of the cluster, and remains a very good scalability up to 256 chips, while others drop its scalability significantly. So note that although this is 256 chips, this is only tensor parallelism. That means if you stack data parallelism and pipeline parallelism, you may scale up to, let's say, million chips given the existing scales of clusters. So as a finally, MeshSlice in 256 chip cluster is 23.4% faster than the state-of-the-art in LLM training here. So also in the paper, there are a lot more details I couldn't cover in this presentation, like how the algorithm is defined in 3 different data flows, or how we can implement memory-efficient slicing by blocking the rows and columns, how we implement and evaluate the LLM AutoTuner to automatically find data flow, mesh shape, and slice count of MeshSlice 2D gem, and also with the additional evaluation results. You can also see in the backup slides. So takeaways here are, first, 2D tensor parallelism is a key for achieving extra scalability of DNN training. But existing 2D gem algorithms have limitations, like collective, they do blocking communication. Cannon has very high traffic because of skewing and square mesh. Summa occurs high synchronization overhead. So we proposed MeshSlice, a new 2D gem algorithm that solves the inefficiency problems in modern accelerator clusters. So it slices the communications into partial AG and RDS communications, which are hardware efficient. As a result, we achieve faster LLM training time compared to baseline distributed gem algorithms. We're only changing the gem algorithm. So you can find the JAX implementation of MeshSlice if you follow the QR code or the GitHub link right here. I'm happy to take any questions from the audience. Thank you.